Hello students, it's right here again. Today we're continuing on Chapter 16, Section 2, Electric Force. Last time we looked at some of the basics about Coulomb's law, found the formulas, and a little bit of basic information on it. Today we're going to do some calculations involving Coulomb's force, and we're also going to do some calculations with gravitational force so we compare electric force with gravitational force. And then next time we'll be getting into the superposition principle. Formulas we picked up last time you should already have written in your notes. If you didn't, get them written down now. We got Coulomb's law. That's our formula here. And with the Coulomb's law, we had our value for our Kc. We're going to need that. And some values we're going to be using, the charges on our subatomic particles and the masses of our subatomic particles. And we'll be using Newton's law of universal gravitation, this formula, G value given to us here. Some problems. Sample problem A. Here we want to find the electric force and the gravitational force. We'll start by trying to find the electric force. So our formula there, and what we just looked at, is electric force is equal to Kc times Q1 times Q2 divided by R squared. So Kc is equal to, I'm just going to use 3 digits here, 8.99 times 10 to the 9th. Going to keep everything in our base units, so I'm not going to write any units down. As always, been this many times, if we're in the base units, everything works out and we get a base unit. If not, we need to switch them to base units. Alright, Q1, mass of electron. Now here we're just looking for magnitudes. The signs really don't matter. So I'm just going to use 1.60 times 10 to the negative 19th coulombs times Q2, but Q2 is exactly the same thing, so we'll square that. In this case, Q1 equals Q2. And then we're going to divide it by R squared. R was given to us up here. So 5.3 times 10 to the negative 11th squared. So our electric force is equal to, run through the calculations, pause the video now, try the calculations yourself, and we get 8.2 times 10 to the negative 8 newtons. So that's our electric force. Then we also want to find the gravitational force. So gravitational force. If you want to, stop the video right now. Try it yourself. Go back, get the formula. If not, not sure what's going on quite yet, watch the video, go a little farther before you stop and try it on your own. So Fg equals big G times mass 1, mass 2, in this case mass of an electron, mass of a proton, divided by R squared. So equals big G, 6.673 times 10 to the negative 11th. Again, we'll keep everything in nice, neat units. Times mass 1 mass of either the proton or the electron, doesn't matter. I'm going to use the electron right now, 9.109 times 10 to the negative 31st times mass of the proton then is 1.673. I'm running out of room, so I'm going to stick it up here, times 10 to the negative 27th. Then we want to divide by r squared. R, same r we had a little bit ago, 5.3 times 10 to the negative 11th squared. Good. If you haven't done it already, stop, pause the video, do the calculations. And then you can start it back up again. And we get for Fg 3.6 times 10 to the negative 47 newtons. So that's our Fg. Just a little bit ago, we had Fn, or F electric force was 8.2 times 10 to the negative 8 newtons. So you can see there, electric force is a whole lot bigger than the gravitational force. So electric force, much bigger than the gravitational force. Yeah, problem number 1. We're trying to find the electric force between this balloon and the denim. So here we're going to have some conversions because our measurements aren't in base units, but our electric force, Fe, equals Kc. Kc, we had just a little bit ago, 8.99. Again, that's plenty of significant figures, so times 10 to the 9th. If we had more sig figs in the measurements given to us, we'd want to add a little more sig figs on this. Times Q1, 8.0, it's microcoulombs. Micro means millionth, so we'll add a 10 to the negative 6th on here. And if one of these objects rub together, charged by contact, gains a charge of 8.0 microcoulombs, the other one loses that charge, so it's going to be also 8.0 times 10 to the negative 6. And then we divide it by the distance between them, 5 centimeters. 5 centimeters becomes 0.05 meters, and we're supposed to square that. Calculation purposes here, because these two things on top were the same, if you want to, we can just call it a square. Then that may make it a little easier on your calculations. Yeah, if you haven't done so, just pause the video, run through the calculations, and you should end up with 230 newtons. And because these were oppositely charged particles, this will be an attractive force. So 230 newtons attractive. Yeah, our next problem. 2 parts here. We're going to find the electric force on one sphere, and then if we connect them with a conducting wire, what's the electric force going to be? Yeah. Problem 2. Again, I mentioned we've got 2 parts here. Part A first. If you want to pause the video and try this one on your own, the answer you should get for part A will be the electric force should turn out to be 2.2 times 10 to the negative fifth newtons. So if you think you know how to do it, stop it, try it, see if you come up with that answer. If not, continue on, or if you don't get that answer, let's look at what I do now. So our electric force, again, Kc times Q1 times Q2 divided by R squared. So electric force, Kc, 8.99 times 10 to the 9th. Here, looking like I got our units of meters and coulombs, so we don't have any conversions to do. Times, charge of one of them is 12 times 10 to the negative 9th. Charge of the other one is 18 times 10 to the negative 9th. And we divide it by R squared. And that would be 0.30 squared. Running all that calculations through, you should get the 2.2 times 10 to the negative fifth newtons. And because one was a positive charge, one was a negative charge, that would be an attractive force. Part B. This time now we connect the things with a conducting wire. So we take the two spheres and connect them together. And then after we get equilibrium has occurred, so after these things are connected together, they're going to end up with the same charge, and they're going to end up with the same charge, and if they started with 12 times 10 to the negative 9th, then negative 18 times 10 to the negative 9th, they end up with a charge of we got to end up with a total charge of negative 6 times 10 to the negative 9th. But then each one of them will have half that charge, so the Q1 and Q2 are going to be both negative 3 times 10 to the negative 9th. Three times 10 to the negative 9. And so that's going to be our Q1 and our Q2. Again, because they equalized each other, giving us a total charge of negative 6, negative 18 plus the 12. Each one of them is going to have the same charge, so it's half of that is where the negative 3 times 10 to the negative 9th comes from. So then plugging all that into our formula, F electric should equal Kc, 8.99 times 10 to the negative 9th, times Q1 times Q2, we just figured out they're the same thing, 3 times 10 to the negative 9th. And we'll just square that. Divided by r squared. The distance is still the same, so that's 0.30 squared. Run through all the calculations, and we should get 9.0 times 10 to the negative 7th newtons. And because these were like charges now, they both had the same charge, this one would be a repulsive force. So the two objects are repelling each other with that force. And then number 3, they give us the force here, and we're going to try to find the distance. I'll give you the answer here if you think you can get it. Go ahead and try it. According to my textbook, it's 0.393 meters. So, stop, try to see if you can come up with that answer. If not, I'll work through it for you. So, again, our base formula was the electric force equal to Kc times Q1, Q2 divided by R squared. If we want to find the R squared, so one simple thing is rearranging the formula, you might remember, so we can always just switch those two. So that gives us R squared equals Kc times Q1 times Q2 divided by the electric force. And then that's supposed to be R squared, not R sub 2. And then we want to square root both sides. So there's our new formula. And if you weren't able to figure that out before, you might stop now and try your calculations and see if you come up with that answer I gave you. So, we're going to have the square root of Kc 8.99 times 10 to the 9th times Q1. Now here we got them in, Q's are in micro. So micro means millionth again. So it's going to be 60 times 10 to the negative 6th times 50 times 10 to the negative 6th, and then divided by the force, which was 175 newtons. And we run through all those calculations. So you run through the calculations, and then square root it. And you should come up with that R being 0.393 meters. So that's a few problems dealing with Coulomb's law and law of universal gravitation. So that's it for now. Till next time, straight again.